welcome to Reason with Science. I'm your host Jitendra. This episode is with Chris Ferrie. He is an associate professor at the University of Technology, Sydney, and Center for Quantum Software and Information. His research focuses on quantum information science. Chris also writes children's books, and some selected titles include Quantum Physics for Babies, Eight Little Planets, and Pandemic for Babies. In this conversation, we talk about beginning of quantum physics, double slit experiment, matter, understanding reality, quantum entanglement, and quantum computing. Enjoy the conversation, share and subscribe to support the podcast. Thank you for listening. Hi, Chris. Welcome to the podcast.
Yeah, thanks for having me.
So, thinking about quantum physics, of course, a lot of physicists, people, they would say that this is like the most successful theory out there, or one of the most successful theories. But then another notion is that we don't understand it. So how much of that part is true?
Yeah, so there's lots of quotes from famous physicists, especially saying that we don't understand quantum physics. I think one of the most famous ones is from Feynman. I think he was kind of riffing on this idea that I can't remember the newspaper that said that there's only 13 people in the world that understood relativity. And he said, Feynman said, well, that's probably not true. Maybe at one point, one person might have understood it. And then they wrote the paper about it. And then if you read the paper, it's quite easy to understand. But he said he could safely say that nobody understands quantum physics, including himself, who won a Nobel Prize for quantum physics. So it certainly seems at odds that all of these Nobel Prizes were awarded for quantum physics, yet they also say that they can't understand it. I guess it depends on your notion of understanding, right? Because all of the technology that we enjoy today, including the technology that we're using to record this, is based on our understanding of quantum physics. So certainly there are some people out there that understand quantum physics, otherwise we wouldn't have this technology. So the question is, what do we mean by understand? And I think there it becomes pretty deeply philosophical.
Although we can always take the example from Richard Feynman, that if I understand something, I can create it. And the fact that we are able to create certain technologies using quantum physics means to a certain extent, we do understand it, right?
Yeah, that's right. Yeah. So he wrote on his board, and if I do not understand, but I cannot create. And yeah, I think in some sense, at the time, there wasn't a lot we could create in terms of like the fundamental aspects and questions of quantum physics. But nowadays we can. During his time, we didn't have access to individual atoms and photons and quantum systems, and nowadays we do. I mean, the Nobel Prize was awarded in physics this year for that very fact, that we can manipulate and control individual quantum systems.
Certainly, there is like a lot of excitement. It was even before in the field, but after the Nobel Prize, I think people are like really talking about the topic. They want to understand, and I think they felt like that it was a validation from scientific community, which is, I don't know, again, it's counterintuitive, but yeah, so that's just, I think how we think of like the validations and this kind of part. But if we I think quantum physics in general, it requires a lot of work, right? Like it's not like we go and listen to or attend few lectures and we'll understand. We need to understand the basics of it, and especially once we start following the history, how it was developed, so there is some sense in it. You start understanding the deeper nature, why we are, or like how we reached at this theory. And the one of the experiment that I can think of is the double slit experiment, which was, I think, the beginning of quantum mechanics, or the understanding of quantum mechanics. So what is this experiment? And let's like kind of start from there.
Well, I mean, the experiment predates quantum physics by quite a few decades. It was first performed by Thomas Young in, I think, the early 1800s to demonstrate that light behaved like a wave. So he wanted to show that, in fact, light wasn't had a particle nature, like say, I think Newton suggested, but it was a wave. So he kind of shone light, or I think it was like sunlight coming through coming through the window, and he took a sheet of paper, whatever, thick paper, poked two holes in it. They're slits, so you cut like thin slits in it, and you let the light pass through. And if light is a particle, then what you should find is two strips of light on the other side. But what he found was a pattern of bright and dark. And in fact, the brightest part was in between where the two slits were. So this demonstrated that light obeys some sort of interference and acts like a wave. And if you did the same experiment with like water waves or sound waves, you would see the exact same pattern. So there was pretty conclusive evidence by early 1900s or 19th century standards. It's about as conclusive as you can get that light is a wave. And then I don't think it really entered back in until into the debate until actually like the 1920s, when Louis de Broglie suggested that matter, which we normally think of as particles, should be associated with wave properties as well. So at the time, Einstein had already shown that light not only behaves as a wave, but also as a particle. And this is what he won his Nobel Prize for explaining the photoelectric effect, that when you shine light on a piece of metal, that electrons get ejected depending only on the frequency of the light, not on how powerful the light is. So he said that, it must be the case that what light is these particles that are hitting these electrons, and when they match the energy, they get ejected. So at that time, we were comfortable with the fact that light was a wave, had wave and particle like properties, but we assumed that matter was just particles. And then Louis de Broglie came along and said, no, like they should be associated with wave properties as well. And this double slit experiment kind of would illustrate that. If you could shoot matter at some sort of plate with two slits cut in it, then either on the other side you see a wave pattern, which is what Louis de Broglie suggested, or you just see two slits of matter behind it. It was many years before we could actually do the experiment, first with electrons, but indeed, of course, we found that it had wave-like properties.
Yeah, which is fascinating. And I think it was actually both work of Einstein and Einstein, as they call it, and Max Planck on black body radiation. That they both started showing that, okay, it's basically the wavelength of the light which matters, right? In the case of, rather than the strength.
Yeah, that's right. So you would expect that, if you shine light on something and it was causing something else to happen, when you turn up the brightness of the light, more of that would happen, but it doesn't. The brightness doesn't matter. It's only the energy, and that's associated with the wavelength. And it's this Planck, Einstein. I'm happy to do it in the Canadian accent. I'll just stay
Yeah.
Einstein. And it was this relationship between the energy and the frequency or wavelength of light that really kind of defines the that core fundamental concept of energy in quantum physics.
Yeah, and the interesting part here is that simply these observations started refuting the classical mechanics, which was, of course, developed by Newton, and it was there all around. But just because the fact that this energy, it comes into packets, and that's what kind of started this was like the initial days of quantum physics, right?
Yeah. So initially, so I think when you learn quantum physics in potentially in high school, but certainly once you get to university, you learn like this historical aspects of it first. And in fact, there's two quantum theories. There's the old quantum theory, which is like Planck, black body radiation, the photoelectric effect, all of these things that happen in the first 2.5 decades of the 19th century, where it was seen as, oh, there's these slight anomalies in certain experiments, and we need to make these corrections, these quantum corrections to classical physics. But at the time, I think everybody thought that, oh, we just need to modify slightly classical physics, and then in the 1920s, people like Heisenberg, Schrodinger, Louis de Broglie came along and said, no, it's actually completely different, and then Dirac and von Neumann created sort of this new mathematical framework. And from that framework, they could predict new things like antimatter and new forces and all this stuff that came after. So in the first two decades, it was all we need to tabulate all the corrections that we need to make to classical physics, and someone's going to come along and have a better clear theory of classical physics and sort this all out. And then in the 1920s, it kind of everything changed, and it became this completely new theory.
Yeah, and what is the quantum word in quantum physics?
What does quantum mean in quantum
Yes.
physics?
Yeah.
Well, so that came really early on. So quantum just means like energy comes in chunks rather than as a continuous quantity. So the quantum is the individual packets or chunks of energy that get exchanged between light and matter.
Yeah. So and then here, basically this double slit experiment showed kind of shown light on matter. The matter can act as both wave and particles, as you already mentioned. So but then this wave particle duality, then it was, I mean, this was like one aspect of it, which of course people start talking about it. The other aspect is the Heisenberg's principle, what he could, I mean, of course, that there is a lot of information there as well. The fact that he had to invent new mathematics to account for these changes, etc. But so what is that Heisenberg's principle, and how much that is important in the case of quantum physics? Still, do we consider this Heisenberg's principle as an important aspect?
Yeah. So initially Heisenberg had this thought experiment. It's called Heisenberg's microscope, and he imagined finding the position of an electron by shooting a single photon at it. But they're of sort of comparable size in some sense, and so if you hit the photon against an electron and it bounces off, you can find out where it was. But now you've imparted some momentum onto the electron. So his original idea showed that you can't measure things, you can't measure properties of objects without imparting some disturbance onto them. So that's sort of that was his original idea. And when people talk about Heisenberg's uncertainty principle, they often think that's what it means, that you can't measure things without affecting them. But it goes a little bit deeper than that. It's still called Heisenberg's principle, even though he didn't make the further developments of it. And what it shows is that it just doesn't make sense to assign properties to things before they're measured. So not only is there some uncertainty in measuring properties of objects? Like when I go to measure the position and the velocity of a ball, there's always some residual uncertainty associated with that, some error that happens that can't be gotten rid of. And that is fundamentally due to the fact that before I measured it, those properties didn't exist. There wasn't predefined values that I'm just revealing through the process of measurement. And yeah, it's a fundamental aspect of quantum physics, and so it's still, it's still always there and relevant today. I think that probably the most obvious place is in quantum cryptography. So if the act of measuring can has to impart something onto the measured system, then when I'm communicating with you, I'm using physical systems. In this case, I'm using uh, electromagnetic radiation between my computer and my router, and then light goes through fiber optic cables under the Pacific Ocean. So somebody could be listening to our conversation, but um, if we if our communication happens with individual quantum systems and they attempt to eavesdrop, then that will be detectable because of Heisenberg's uncertainty principle.
Oh, that's interesting. So it'll be some sort of inference that will be able to get it.
Yeah, so we can, I can send you some sort of test information, and then we can just call each other up on the phone and say, "Hey, did that work out?" And if it didn't, then we know that somebody was trying to interfere. Whereas with the way that we communicate today, information is so redundantly encoded that I can just look at it and copy it. Right, it's like copying information from a USB stick. That you don't know how many times it was copied, right? Whereas with quantum information, it can't be copied, so you can detect that the presence of an attempt to do that.
So you mean if they are listening to us right now, we can tell them that, okay, we are talking about quantum physics, and one day soon, the technology will evolve and they should find
Well,
better jobs or something like that.
at the moment, yeah, I mean, we're recording on Zoom, which the little blue, the green shield with the check marks says that this is an encrypted conversation. Although you're going to post it on YouTube for everyone to see anyway. But at the moment, in this instant, it's encrypted. But so that means that somebody could copy and keep a copy of that encrypted communication. That's I mean, I'm broadcasting it over the Wi-Fi, right? So, but the thing is that we think that problem of trying to crack this encryption is very difficult, and so that's why we believe that this is a secure conversation. But maybe we can get to this later in the conversation. If we could build a quantum computer, that would no longer be the case. And, and maybe in 10 years' time, someone could take that encrypted data and unlock it.
Yeah, certainly we'll talk about that in the later in the conversation. So and then when we are thinking about this Heisenberg's uncertainty principle, the next step which comes is from Schrodinger, who gave the so-called or the famous equation is the wave function or Schrodinger's equation. So how does that relate to quantum physics? I mean, so far we use it in our theories, in our calculations, right? I mean, people they are thinking, or at least this is also accepted, that this, if there'll be some theory of everything or something like that, Schrodinger's equation will be part of that, or something like that. So what's your thoughts on it?
Well, yeah. So around the same time, Heisenberg invented matrix mechanics to account for his uncertainty principle. And then around the same time, Schrodinger was looking at Louis de Broglie's thesis, where he talks about the wave properties of matter. and said, okay, well, if it's a wave, then it ought to have some wave equation associated with it. And so he went and found out, devised this wave equation. And both in Heisenberg's matrix mechanics and Schrodinger's wave mechanics, there were complex numbers. And so you could see a relationship between them. But people didn't agree or know which one was right and which one was wrong. And then later, Paul Dirac came along and said, well, there's a more abstract set of mathematics that encompasses both of these. Like, these are just two sides of the same coin. It's really just two different ways of looking at the same abstract thing. And that sort of was like the final straw in quantum physics, where it just became an abstract theory with complex numbers.
Oh,
so there's no like there's no special status for Schrodinger's equation. It's just one particular way to write down the abstract mathematics.
Yeah, but then this does give us like the other properties of quantum physics, like quantum superposition or quantum entanglement. Is it true?
Yeah, so we usually talk about quantum physics in terms of like what we say is the Schrodinger picture, that there's this wave function. It starts at a particular time and then evolves according to Schrodinger's equation. And, it can develop properties like superposition and entanglement and these other things. Those are just particular kinds of wave functions that your initial one might evolve into. That one's probably, Schrodinger's picture is probably the most popular. And, it's the one we use in quantum technology, but, it's not a continuously changing wave anymore, but things change in discrete chunks, just like in a regular computer, where there's a sequence of steps that happen, and there's a two steps you can take to create entanglement or superposition. It's all very kind of simple and straightforward in the context of quantum information and computation.
Yeah, I definitely want to talk about quantum information part. But what is quantum superposition and quantum entanglement?
Well, they're kind of labels that we give to certain mathematical objects. So when I teach quantum computing, so I teach quantum computing to computer science students. They have no background in physics whatsoever. So I have to teach them about superposition and entanglement. And the way I do it is, I guess you could say somewhat inspired by Feynman, is I have them create it. So they write quantum software to create superposition and entanglement, and then they can run those on quantum computers that exist in the cloud. In fact, one of my students emailed me, who has since graduated, and said, they're computer scientists. They just took the one quantum information class as an elective, and they said, I'm so glad I took your class, because I saw the news about the Nobel Prize and all of the stuff about how confusing it is. But in your class, I wrote a Python program, and I coded entanglement, and I ran it in Python, right? So it's not surprising to me. So I think one way to think about it is that in quantum physics, we can represent our information with classical labels, like conventional labels, like a particle is definitely here, or it's definitely over here. So I can write down my information with classical physics. But there's a rule in quantum physics that says two states of information can be just mathematically added together, and that's another valid state. So that's true of all waves. If I have a water wave or a sound wave, then I can add two waves together and I get a new wave. So in quantum physics, the waves represent my information, and one state of information can be added to another state of information, and that's another valid state of information. And so if I've labeled two pieces of information with classical labels, and then I add them together, that's usually what's called a superposition, because I've kind of gave them these special labels at the outset. But that new state of information is just another state of information. So that's superposition. Now, the classical information can contain correlations, like the particle is on the right and it's blue, or it's on the left and it's red. So those are two classical states of two classical labels I can place on the states of information. Now, if I add those together, I have a superposition, but they contain correlations. So entanglement is just superpositions that contain classical correlations.
That's interesting. But I mean, of course, once people, they put it in like even simpler words, they generally, it is put it like, okay, there are two particles separated in space and they are linked to each other. That's quantum entanglement. Um, but so what you are saying, that we see it in this way because we are still using classical sort of semantics rather than thinking of it in a better way, or explaining it in a better way.
Yeah, I think the information theory perspective is sort of the, that's the ultimate perspective, and the one, you should really just take, because if you say well, first of all, there's no such thing as particles, right? According to our best theory, there's only fields. Particles are excitations in fields. So, if you try to take this sort of, traditional explanation where you talk about particles, then, already at the outset, you're making a category error. So, and then it obviously leads to confusion. So there's no particles and there's no physical link between them. That's not real, right? I mean, that at best is an analogy, but it's a bad analogy because it immediately leads people to sort of supernatural thinking.
Yeah, but then once we make the measurement, because that's I think, another layer here, um, you see particles, right? Like this is what you are seeing, or like, how do you look at it then? Is it now another updated information element or something?
Well, so ultimately, the way I view quantum physics is it's an operational framework. So it is a set of mathematical rules that allow you to describe in operational terms what happens when you do experiments. And what I mean is there's really no wave function or quantum state. There's just a prescription for what you need to do if you enter a lab, like which buttons to press, which knobs to turn, how to build it, right? That's what a quantum state is. It's a list of instructions to create an experiment. And the same is true of a measurement. And what quantum theory does is it takes these two lists of instructions and gives you a set of probabilities for the potential outcomes that you'll see. And those are just things that when you go and you write it down, it's you're already writing down your expectations for what experiences that you're going to have, right? So in the double slit experiment, my experiences are little little blips on a screen, right? And or you can just have an imaginary device that has two lights on it, and one of the lights goes off or the other light goes off, and that's the result of the measurement. If you go into a quantum physics lab, you can't really point to where the particles are, right? You have equipment and a data stream, right? You don't observe particles, right? You observe voltages on a spectrometer and a stream of data that's filtered through a bunch of electronics. And quantum physics gives you really accurate predictions for the outcomes of these experiments, but it says nothing about what's real, what reality. In the rules of quantum physics, there's no particles, there's no photons, there's none of this stuff, right? That is sort of out a layer of interpretation that we put on top of quantum physics.
Okay, this is interesting. So we are already going there where I wanted to go, of course. Um, okay, so then let's talk about what is matter, because this is where then things go or things become more complicated, and of course people can take it in a different way. Um, so because we are, I mean, of course we are using these theories to develop technology, etc., but then other goal is to understand the nature of reality, right? And from our reductionist point of view, this is what we want. What are the fundamental forces, what are the fundamental particles that they come together and form everything that we see around us? So how do we then look at matter? How do we look at those, or how do we find or understand those fundamental forces? Of course, like, I think even you would agree that quantum physics is one of the successful theories, even to describe the complexity, the emergence that we see around us. So either it is missing something, or you think that that we, or like, I don't know, like how or where we can go with this in terms of understanding the nature of reality.
I mean, it's a good question. I I I don't subscribe wholeheartedly to the reductionist philosophy that it will actually lead to something fruitful, to answer questions that we actually want answers to. So what is one? Well, I mean, we already see this with quantum physics. Let's take quantum physics as an example. Um, let's suppose that there are no unexplained phenomenon, right? Quantum physics is the end. There's no dark matter. There's no black holes. There's no Big Bang at the beginning of the years. So we just have quantum physics. It explains everything. But we still wouldn't use it to describe, the real questions that matter to us. Like, why am I here in the first place? What are these experiences that I have? I think a more concrete example is just, traffic in the street. Would it ever make sense to describe traffic in terms of all of the particles and forces that happen between all of the things that the cars are made of? No, that would never help, right? Traffic isn't contained within the laws of quantum physics, yet that's still an important concept. So, I think this was sort of popularized by Anderson, in his, I think in his Nobel lecture, and he said, more is different, right? That you have these hierarchies of theories, and he rejected this reductionist view that if I know everything about the constituent parts, then I can just derive what will happen at the higher level. And that's just, I mean, we see that that's just not the case already. So if it's already not the case, why are we continuing down this path? Like, I agree, reductionism has served us well in many situations, but it isn't the be all and end all.
So what you're suggesting that the people at CERN, they should be cautious now, like where they can go afterwards, or in general, like this thinking about matter, what is matter, and nature of reality. That these are just philosophical questions, and we shouldn't continue down that line.
No, what I'm saying is that the answers to these questions won't be found in reductionism. as I said, we understand quantum physics really well, and with this model that that there are these fundamental particles and the fundamental forces, and that's all there is, and they go together like Lego blocks to build all the stuff around us. We don't use that to decide what to have for breakfast, to debate what it means uh, to see the color red, right? It's not useful for these things, right? Like I don't know where the limitations are. I think there's still lots of fruitful things that we can use this theory for, but it there are these levels of complexity, and at higher levels you need a different theory that's relevant to that level, and you can't simply derive meaning at higher levels from fundamental laws at lower levels.
Yeah, but is there something important down there or no? Like that's I think, because of course, once we look at the emergent phenomena, we will not be able to explain everything. I mean, of course, you explain the traffic part, but then apart from that, even if we look at from our materialistic point of view, we won't be able to understand psychology from quantum physics or economy and this stuff, right? Which is, of course, I mean, there is a Nobel Prize this year, but then we are hearing news about inflation and everything, so that we can already understand there. But then, yeah, the question is, because like the people who are working on this stuff to understand the nature of matter, I mean, definitely there is a lot of scope in terms of technology and engineering, but in terms of basic science, as they call it, do we have some fruits there, or we are just roaming around?
I mean, they're questions, right? And some people want them answered, and that's the nature of science, right? That that science progresses because people have questions that they are compelled to answer. I'm not suggesting that they don't answer them, and I don't know what will come of those answers. But a theory of everything won't make biology irrelevant, right? It won't make psychology irrelevant, and I think that these questions are far more interesting. I'm not interested in a theory of everything. A theory of everything will just be another chapter in a textbook about physics. It's not going to tell me why life exists.
Yeah, that's interesting. I think Sean Carroll has similar views. So what he talks about is the fact that we already have the standard model in physics, means this is so we already have discovered or uh, found the forces and the particles which are important in our daily life and in the daily world. So it's not like that we will find something which will explain um, s- something more in terms of our daily understanding. It's just that, okay, whatever we will find now, that will just help physics or in general, like our thinking beyond our daily lives. And so it's not like it's going to impact the way we or in the world that where we live and how we see world, etc.
Yeah, I totally agree with that. I go one step further, and I think that many people they have these deep questions, like they want meaning in their life. For example, they want to know, what does this mean? And they think that, well, maybe the next revolution in science, like the theory of everything, for example, is going to give us that, right? It's that, what it's the one thing that we don't know, so it must be the answer, that it must contain the answer that I'm searching for. Um and and so it's not just our daily lives, but also like the deep questions that we all have, uh, that won't be answered by a theory of everything.
Yeah, the only point which I think that we don't understand much. And this is something I think also really important to even understand biology, origin of life, etc. Is the fact is the science of chance, luck, chaos, we can call it. So all those factors, like how do they get affected? Because I think this is where we are not able to progress much. I mean, the fact that we can't predict weather for next few days in like so much accuracy, which should be like simplistic than I don't know, understanding psychology or economy or something. Uh, so that shows that something like this is what we lack. So I don't know if we really need a theory of everything, but we definitely need a theory which will kind of account for this chance events or luck or chaos. How difficult it is, I don't know. I mean,
Well, I mean, I guess you could take as an example, say flight, right? So when you think about flight, early on, people were looking for, just some object that would stay stable in the air. But, they didn't have chaos theory at the time. But as you know, like turbulence and things quickly make things go out of control. And what was the solution? The solution was control theory. That's what the Wright brothers were famous for. They gave control to the pilot. They made an aircraft that was fundamentally unstable. It wouldn't fly on its own. It needed a pilot to correct with feedback for errors. So, if we want to get into science fiction, then I think, we're not going to find a way to predict the outcomes of chaotic events. That's sort of that's the definition of chaos, right? But we can be clever engineers, and what we can do is we can turn chaos into stable environments.
yeah, that's interesting. So so that means it goes into a little bit of like understanding what is chaos. Are there like just the factors which we are missing in our models that we need to include, etc.? Like the understanding of chaos itself, right?
Well, I think the principles of flight don't rely on the fine details of every air molecule, right? Uh, so there's obviously for any aircraft there's failure modes, but the idea is it's sort of independent of the model of say the air around the airplane, right? So the control laws that are used to enact the feedback to make sure that the plane stays stable are make assumptions about what the environment is. But those are really, really weak assumptions that you don't need to know the fine details of them. Of course, if you were if you were an adversary in that scenario, then you could make sure that it doesn't fly. But I think that's sort of the point, right? Is that you can get rid of all of the details that cause it to be chaotic with the this mechanism of control.
Yeah. And so since we were also talking about quantum information, so what do you mean by quantum information?
Well, so quantum information is a way to represent our knowledge with vectors. So normally we represent our knowledge with with numbers, and usually these numbers are bits, ones and zeros. So the digital computers utilize this representation of information, ones and zeros. But that's not the only way to do it. There are other ways to represent information with different mathematical objects. So you can have continuous numbers. So old analog devices would use gears, right? Gears and pulleys and things. And so that's a continuous numbers. In quantum physics, we use vectors. So these are lists of numbers. And the numbers happen to be complex numbers. So those are just kind of a different set of numbers. So you have these lists of complex numbers, and you turn one list into another list, and that's the process of changing that information. Now, it's not, in some sense, it's not fundamentally different than digital information, because simply by telling you, describing it to you, means that I can represent it with digital information. It just so happens that it takes a lot of digital information to represent quantum information. So it's sort of a new compact way to represent certain states of knowledge.
And then where does the probabilities here account? I mean, are there is it like really binary, or there are gradients here?
So I have a list of complex numbers, and I can manipulate that list of complex numbers according to a set of rules, and that would be an algorithm. So if I can take a list of complex numbers and I can change it in certain ways, then I've created a quantum algorithm. And I can, there might be some problems that I can solve faster using a quantum algorithm than I could with a conventional classical algorithm. And that is indeed the case. So the next question would be, well, that sounds terrible to do by hand. Couldn't we just build a machine to do that for us? And yes, you can, because quantum physics gives us a set of things in the world which naturally encode these vectors, these complex numbers, right? So it's photons and atoms and all these quantum things. So the probabilities come back in, because in order to read that information, I have to measure the quantum system, which involves the probabilities. So, of course, we have this theory of quantum information that includes that as a constraint, that you can't just read the list of numbers. You only get one of the numbers with some probability, because the only way we know how to build machines to automate this process for us is with the rules of quantum physics, which say that you can't do this without invoking probability at some place.
I think here we can also briefly describe what are complex numbers.
Well, complex numbers. So I think the easiest way to understand complex numbers is as a pair of two real numbers. So a real number is just any number on the number line. So not integers, not fractions, but everything in between those. So from minus infinity to infinity, all the way through zero, all your decimals, those are the real numbers. So if I take those numbers and I take a pair of them and I create a new rule for multiplying pairs of numbers together, then I've created what's known as a complex number. And they were just invented because it's a convenient way to represent waves. So it's not just used in quantum physics, it's used in like electronic engineering, because it just makes things that deal with waves easier to calculate.
I mean, the example would be the particle antiparticle combination, right? Like taking the example of electron positron combination.
Well, I wouldn't say that there's a direct mapping of complex numbers to things in the world. Because you can write down all of quantum physics without any complex numbers. It's just inconvenient. So in some sense, they're there because of convenience. Yeah. So it's just a new like real numbers themselves. You can't go out in the world and find real numbers, right? So far as we can tell, the universe is discrete. That's what quantum physics says. So there's no real numbers in the world. It's a mathematical convenience that makes things like calculus easier. So these complex numbers just make kind of calculus with waves easier.
Yeah, so since you mentioned about quantum information theory, I think here the information part is also interesting because, of course, then philosophers, they argue that, if there is information, means already the mentation part, the consciousness part, it enters in the picture. Means because it requires consciousness to make, because that's what like information is there, right? um what's your comment on that?
Yeah, it's information only has meaning to us, right? So in some sense, information was born when the first human decided to communicate with another one. Uh, it it's only useful to us if some alien civilization found a hard drive. To them, it would be just meaningless nonsense, right? It's only a useful concept to us, and so I guess that's the connection, I suppose, between the subjectivity of experience and consciousness and information.
So then here let's bring the other people also. That so I mean, I've interviewed at least two guys, Bernardo, Kastrup, and so he's a philosopher who talks about the consciousness is fundamental in the nature, and Donald Hoffman, who
Mm,
talks about that space-time is not fundamental, and there is something beyond space-time,
mm.
and again it's consciousness which is fundamental. So what are your thoughts on this? I mean, so one perspective is this, the way you said it, that okay, there is some information, but it only makes sense when we kind of start conceiving it, or so of course then there is consciousness, but then stretching it to the extent where we kind of take it intuitively that okay, consciousness is fundamental, that's why the information evolves in the universe. What do you think, if it's true or if it makes sense or not?
Yeah, I mean, I think we're stretching language pretty thin at this point, right? I think um, we get beyond science, and by science I mean like coming up with testable hypotheses, right? Into philosophy, and that's not bad, but I would maintain that every philosophical statement you can say with clarity is going to be wrong, because um, just it's just a matter of language, right? Language itself is not sufficient to come up with definitive answers to questions, right? The purpose of language is to communicate between people. Um, but what do I know for certain is that I have experiences. That's I think that's the limit of it. Um, I see on my screen you're a two-dimensional object, but I can create in my mind a three-dimensional image of you. Um, it's useful for me to assume that you're kind of like me and you have experiences as well. And then that gives me expectations for how you're going to act and how we might interact and what we might agree upon. And then, I extend this to all of the people around me. And then now I have like this network of people that, uh, seem to have experiences and expectations. And where those line up, that's kind of just what we call reality. Right? It's just our inner subjective agreement about our experiences. Uh, and I think that's it. To me, that's sort of like all we can say. And beyond that, I don't think we have the tools at the moment, and maybe we never will, to explore beyond that point.
Yeah, but the people who kind of know about quantum physics, and they have tried to stretch it, in different words like terms. Quantum consciousness is one example, uh, and I think from the historical point of view, one of the scientists who actually mystified it a bit more with, so it was this Wigner's friend's experiment, right? So let's talk a little bit about that. And if because I think now a lot of studies, or some studies that they are coming, which kind of refute his idea about it, right?
Yeah, so I think you start with Schrodinger's cat, right? So you have the Schrodinger's cat paradox, where there's a cat, it's in a box, there's a vial of poison and a atom that may or may not decay, and a Geiger counter which hits a hammer, breaks the poison vial, and kills the cat. So because of the randomness of quantum physics, you have to assign this superposition of decayed and not decayed to the atom. And that means that there's a correlation between the atom being decayed and the cat being dead, because the decayed atom set off the Geiger counter and broke the vial. So Wigner said, okay, what about if I put Schrodinger and his box inside of a bigger box, and then I ask about what happens to them, right? So for Schrodinger, inside the box, he has an expectation. He's going to open the box, find a live cat or a dead cat. And so his state of knowledge has to be in superposition as well for the person outside the box. And this is sort of like the contradiction, I guess, because Schrodinger is not in superposition. He has definite experiences, right, about classical things. So how could his mind be in superposition? So for some people, I think this just illustrates the idea that these states that we're assigning to things are really states of knowledge, and it doesn't matter that there isn't one right answer to the correct state. It really depends on the context. So for Schrodinger, he is free to assign one kind of quantum state, and for Wigner, yeah, normally it's Wigner in the box, and then Wigner's friend is watching him. For the person outside, they can assign a superposition or an entangled state to what's going on in their bigger box. And that's all consistent, because if everybody just assigns quantum states according to their expectations, then this is where quantum physics is successful.
Yeah, but then where is mysticism in this?
Well, I guess the question people pose. So some people want to say that these quantum states, right, are they are the things, they are the things that are real, elements of reality. So it's when you do that, then things become weird. So if I say the state alive plus dead is real, then that seems mystical, right? Uh, is it alive and dead at the same time? Do I have to introduce many worlds? This is where the mysticism comes from, when you attempt to be a realist and say that the state is associated with like some ontology, some elements of reality. But if you say that quantum states are just our own individual private expectations for what will happen when we do experiments, then you don't get into any problems. But most physicists don't like this. They think they want more, right? They want to know, they want to know what it says about reality. And people like Niels Bohr said, that's not the job of physics, isn't to describe reality, right? It's to describe stuff that happens in experiments.
Yeah. So so here I think the interesting part is the fact that most of the physicists they don't talk about is the decoherence part. So the fact that in most of these thought experiments, first of all, we there are always this kind of sentient beings, either cats or humans. Instead of uh, thinking of particles, you kind of directly replace the sentient beings, and you then kind of mystify it, right? But on the other hand, this is reality in the sense that what we observe, we kind of observe this more like classical world. We don't really observe the quantum world or things here and there and all that stuff, right? So this gap is, how do we cover this gap?
Well, in experiments, we do, in some sense, cover it. So I would say that quantum physics is a set of models that work really well in the following situation. When you can identify some phenomenon that is extremely well isolated from any other environment, and that makes sense for atoms. Like on the scale of an atom, it's mostly surrounded by empty space, right? The distance between atoms, at the scale of an atom is huge, so it's well isolated, and that's why quantum physics works well to describe it. From this point of view, of course, you could never do Schrodinger's cat experiment, because if you isolated it from its environment, it would surely be dead, right? And ultimately, that's why quantum physics will never be relevant for us at the macro scale, because we are reliant on the environment that we're in. So if I take a system and I isolate it, then it will be really well described by quantum physics, and you'll get superpositions and all of that stuff. If there's an interaction with the environment, then it starts to take away information from that system, and that's what's called decoherence. And in experiments, we can probe this transition. We can watch, in some sense, watch the quantumness turn into classicalness as a function of how much information is being sent out into the environment.
That's interesting. So I think here probably it's a good time to talk about quantum computing, where you use quantum information. And so how far we can stretch. First of all, let's simply talk about how do the quantum computers look. So we have a few of them all around the world. What I get right now.
Yeah, I mean, we've lost count now. I mean, there's quite a few. They're all small. So the fundamental unit of information that we use in our digital electronics is the bit. And around the early 90s, I think, the qubit was coined as the fundamental unit of quantum information. So all quantum information can be represented as some number of these qubits. And so these are, again, these vectors of complex numbers, so lists of complex numbers, but there's only two of them. So it's a vector that only has two entries. And all other quantum information, no matter how big the vector is, you can write as a bunch of these two number vectors. The computers that we have today are, in the sort of 5 to 20. So there's public access to quantum computers that have 5 qubits. And then if you pay a little bit more, you can get access to ones with 20. And then there's some like research grade ones that may or may not have like 100 qubits or so. So that's sort of the state of play at the moment, 2022, October.
So this qubit means the complexity. I mean, how does it help in thinking or replacing binary bits that we use in our normal computers?
Yeah, so two complex numbers with, say, 32 bits of precision requires 64 bits. So that's 8 bytes. So that's not a lot. 8 bytes is not a lot. I can represent a qubit with 8 bytes. But the issue is every qubit that I add doubles the requirement. So by the time I get to 30 qubits, then that's 4 gigabytes, right? And that's probably the limit of the RAM of an average computer these days. So if I get to 100 qubits, then I require more bytes than all of the classical computer memory that exists in the world, right? Because it doubles every time. So that's sort of where the efficiency and capacity in qubits comes from.
So what does this mean, that all the classical computers means all of them combined together, or it's just that you're talking about the space that we have in one sort of classical computer?
So because it's information, like I can represent it sort of virtually, right? So the information that I see on my screen right now, like your face, doesn't map directly to transistors in my computer. Like it's virtual information. A lot of all of the components of the computer come together to create it. So I can create a virtual quantum computer with my mobile phone that has 30 qubits. But if I wanted to represent a 31 qubit quantum computer, I'd need 2 mobile phones. And if I wanted to represent a 32 qubit quantum computer, I'd need 4 mobile phones. 33 is 8, right? And you can see that the doubling happens quite quickly. And by the time I get to a 100 qubit quantum computer, I could virtually represent that, but I would need all the mobile phones that exist in the world to do it. Or I could just naturally represent it as vectors with 100 quantum systems.
This is interesting. So how big is these quantum computers?
Yeah, so IBM and Google are sort of at the forefront, and they have around 100. So but the problem is that they're not perfect. So they're very limited in what you can do with them. So it's not as if that technology has surpassed conventional technology because of how noisy the environment is. Remember, for it to behave in a quantum mechanical way, it has to be isolated from the environment. And they try really hard. Like they put them in what's called a dilution refrigerator with liquid helium, which means that it's 1,000 millikelvin, which is like thousands of times colder than outer space, right? It's the coldest place in the universe, and still there's environment that is corrupting these devices. So it's a huge challenge to isolate them, and again, that I guess this is where the idea of control comes in. That rather than trying to just isolate them, what we need to do is actively correct the effects of errors that come in from the environment.
And the errors are basically, or can we just simply call it a collapse of the wave function? Because I think that it loses this kind of quantum properties once it's observed somehow. Like,
And no, it's not quite the same as that concept of collapse. So it's what happens is the description of the quantum information so initially you want it mapped on this device that you have isolated, but there's some environmental interactions, and so the information gets mapped to something in the environment, but you can't keep track of it, right? It's some cosmic ray that flew in and interacted with your device and then flew off in the other direction. It's not like you can go track that down to get the information back. So you can't copy quantum information, and so as soon as a piece of it leaves the device, it's gone forever. And so the this happens quite quickly, on millisecond timescales in today's quantum devices. So we can't keep the quantum information, in some sense, alive long enough to do any quantum computation that would show an advantage over conventional electronics today.
So basically, let's say if we encode some information in few particles, and as soon as these particles they leave, they can simply interact with the other particles which don't have this information, but then it just gets messed up, like on the way or something. Is it?
Yeah, so you have two particles in the there, you've somehow correlated them, right? Like you said, particle antiparticle, for example, right? Or we'd like to talk about spin, or it could be anything. They're correlated in their properties, and if one of them interacts with an environment, then the other one is now correlated with that particle in the environment. So if you want to, if you're familiar with the language of entanglement, then you say at first the two of them are entangled, but one of them interacted with the environment. Now one of them is entangled with a particle in the environment, and that particle is lost. And so what you're left with is essentially, random, just random, which is not information at all.
Yeah, so I think here we can talk about this year's Nobel Prize in physics, because it was given for both quantum entanglement and quantum information. So the work of John Clauser or Alain Aspect or Anton Zeilinger. Um, so first of all, like, what's your view on the Nobel Prize? Maybe it was already needed, but like, what do you think?
Yeah, I think it's well deserved and yeah, overdue. I think it sort of culminated in Zeilinger's experiments in the late 90s. So uh, you could have given the Nobel Prize back then. um, it's you can really see, if you're kind of in the community, that there are these sort of cliques, and quantum information wasn't seen as physics for a long time. Nowadays that's changed, and so and for many people who went through those decades where their work wasn't seen as part of physics, this Nobel Prize is in some sense validating. But for younger people, I mean, I'm not that young anymore, but certainly much younger than Clauser. Uh, luckily we didn't go through that, right? When I did my degree and finished in 2012, it was a sort of, it was a hot field, right? And there was, it was kind of already seen as a legitimate field of physics and science.
Yeah, let's talk about at least the experiment done by Zeilinger, because I think he really nailed it down to the point to kind of show that entanglement is true, and then there is this information, or there can be information encoded in two particles which are separated in space.
Yeah. So I mean, we can. Zeilinger did a lot of experiments in entanglement. So Clauser did one, maybe two, and Aspect did, at least in terms of the Bell inequalities, which was cited in the Nobel Prize. He maybe only did a few experiments as well, and then Zeilinger came, a decade and a half later, and it redid those experiments to higher and higher precision, but then also used those experiments to enact quantum information protocols like quantum teleportation and these sorts of things, and that's why the Nobel Prize says applications in quantum information science. That was Zeilinger's part. Like, he took these fundamental experiments and said, what? Wait a minute, we can use these things to achieve technological advancement right? And so in the late 90s, and what he's doing now is developing this fundamental science to eventually realize a fully sort of quantum internet, a quantum network.
Yeah, which is to some extent it's already being used, right? Like there are systems which especially in China, that there is a system that they could develop, and they could use this system miles away, and could use it for the information transfer, etc.
Yeah, I think it was. I mean, I don't know if it was Zeilinger group specifically, but there was the sort of quantum satellite community. They demonstrated quantum communication between Vienna and Shanghai. I think it was Shanghai via satellite link. So yeah, I mean, it's still very sort of nascent technology, but the proof of principle experiments are done, right? And to someone of my generation, none of it is surprising. I mean, it's like being told that the sun is the center of the solar system, right? It's like you have this theory, it's incredibly successful, so all of the predictions shouldn't be surprising. Right?
Yeah, one thing which is revolving around these experiments and the idea of these technologies is the fact that it can boost a lot of speed, and of course the crypto part that you mentioned before. So how much reality is there?
Well, again, we know just from mathematical fact that if you can uh, manipulate this quantum information, yeah, not if you can, but if you manipulate quantum information in a certain way, then you can solve problems with fewer steps than you can if you use digital computers. Yeah, so that's just a mathematical fact. There's a website. It's called the Quantum Algorithm Zoo, and it has like 65 mathematical problems that you can more efficiently solve using quantum information than classical information. Um, so yeah, that's what quantum theory says. So like, if you believe quantum theory is true, then it's not. There's no question, right? It's just a matter of engineering to build the technology to enact the control necessary to automate it. And you can do the calculations by hand. It would just take you a really long time, and nobody wants to do that. And yeah, humans are probably more prone to errors than machines. So yeah, if we build the machine, then it'll be faster. It's just another prediction that will eventually come true about quantum physics.
Yeah, this is like fascinating. So most of the concepts that we discussed today, I mean, it's we can already think, and I'm sure there'll be few comments that it's all complicated, etc. I mean, of course, we didn't talk about equations and stuff most of the time, but in your case, you write about these concepts for babies. So
Right.
what's going on there?
um, yeah, I think it's a bit tongue in cheek. Obviously, there's no babies taking quantum physics exams. um, I think it serves an important place in early childhood literature, in that, like you said, a lot of people think it's really complicated, and it's somehow reserved for people with PhDs. But I like to think of it more like music, right? So you have classical music. Nobody enjoys classical music the first time they hear it. You have to like want to enjoy it. You have to study it to really kind of understand what joy you should get out of it, right? But then there's pop music, which everyone likes pop music. Um, so we have the complicated version of quantum physics, but we don't have the simple version that everyone can understand. And I think everyone should be able to understand the basic things in quantum physics. And so in the books, we don't go through all the details, and we certainly don't go down philosophical rabbit holes, you know, giving infants existential crises. But you know, we talk about the basic things. So in quantum physics, you know, where does the word quantum come from? It comes from the fact that energy is transferred one chunk at a time between matter and light. And there's a quantum computing for babies. And I just talk about the same thing I mentioned to you. Is actually the same analogy, that you can represent the information contained in a molecule with your mobile phone, but the bigger the molecule is, the more phones you need. And if you want to represent my favorite molecule, which is a caffeine molecule, then you would need all the phones in the world, right? So it's just these, you know, little kind of fundamental concepts and facts and analogies with pictures, so that, you know, people can have at least a little bit of knowledge about these things.
Yeah, I think it's a great idea because also to kind of develop that kind of curiosity even in like these growing children, it'll be interesting. I mean, if they are asking these questions, certainly teachers will start working more in their lectures and stuff. So that's that's definitely helpful. So yeah, so thank you so much for the conversation. I think we covered a lot of territory. A lot of information is there. I think more than the quantum information, but we'll see what people think about it. So thank you so much for doing this. It was great.
Yeah, thanks for having me.